This integral is absolutely amazing because solving it combines so many different methods of calculus, like improper integrals, integrating by parts, applying geometric series, using L'Hopital's rule, and in the end getting a number theory result, because the whole integral is equal to -2 times the zeta function of 3. So let's just jump right into it. And as I said, we are dealing with an improper integral, so first we take a look at the limits. If x and y would both be 0. Then we have a 0 as an argument for the logarithm, so it's minus infinity, so the integrand is no longer well defined at this limit of the integral. Now let's take a look at the upper limit, x and y being equal to 1. Then we would have a 1 for x, y here in the denominator, and 1 minus 1 is 0. Dividing by 0 gives us a problem, so the integral is also not well defined at this limit. So we have to treat it as an improper integral, so what we will do is use a different color. We will have the limit, and we introduce some parameters like alpha to gamma and beta to delta, and then we have alpha and beta going to 0, and gamma and delta going to 1. And then our normal integral log of xy divided by 1 minus xy dx dy. And now we can solve this integral because x and y, they are now in the area between 0 and 1, with 0 and 1 excluded, and the integral is well defined. Which already brings us to the next cool trick that we will apply to solve this integral, a trick that is very similar to a trick that I showed you in a previous video where I solved the Basel problem applying Tom Apostol's proof on it. He used a similar integral like this, and what he said is that 1 divided by 1 minus xy looks a lot like the solution of a geometric series. So a geometric series starting at n equals 0, going up to infinity, and x and y being powered to the n. So this is converging if x and y, the product of both, is in the interval from 0 to 1 with 0 and 1 excluded. And if both in x and y are in this interval, then the product of them is as well. So what we can do is we can plug that into our integral here. So we have the limit of alpha beta going to 0, gamma delta going to 1, and then we have alpha beta gamma delta times the sum going from n equals 0 up to infinity of xy to the power of n times log of xy and then dx dy. So since this sum is converging, we can just extract the sum sign out of the integral and in front of the integral. So let's put the brackets back here, and voila. And what we have to do now is solve this integral with respect to x and with respect to y. And the first thing we do is solve the integral with respect to x, which will be this integral here. And why we treat this as a constant. So this got a little bit confusing. Y is the variable, so y to the power of n, we will be treating this as a constant. So let's have a look at this integral. So we have beta going to 0, delta going to 1. Integral goes from beta, not to gamma, to delta. Then we have x to the power of n, y to the power of n, times the log of xy dx. And now we use the integrating by parts method. So if you remember, oh, what is happening? All right. That was shocking. So integrating by parts is we have an integral over u prime v, where u prime is the derivative of u, and this is equal to uv minus the integral of uv prime. I'm sorry. And now we have the limits a and b, so we evaluate this at b and a, and here the integral goes from a to b. And similarly, we will say xn, x to the power of n, and times y to the power of n. This is our u prime. This means that u is y to the power of n times x to the power of n plus 1 divided by n plus 1. And our log of xy, this is just our v. So let's solve this integral with integrating by parts. So we have the limes of beta going to 0, delta going to 1, and then we open the brackets for our two terms that we get from the integrating by parts. And the first term we get is y to the power of n, x to the power of n plus 1 divided by n plus 1 times the log of xy, and the whole thing evaluated at delta and beta, minus the next integral goes from beta to delta, and now we have u, which is y to the power of n, x to the power of n plus 1 divided by n plus 1 times the derivative of the log, which is just 1 over x dx, and we close the brackets. All right, so let's have a look at the brackets. So we have the limes of beta going to 0, delta going to 1 of yn x, or not, let's plug it in already, delta to the power of n plus 1 divided by n plus 1 times log of delta y. So we can just drop the beta here. All we're interested in is the delta going to 1. Then we have minus the limes, the limit. Now we have beta going to 0, y to the power of n, beta n to the power of n plus 1 divided by n plus 1 times log of beta y. Okay, I will not write the solution to this integral down yet, because first I want to deal with those limits here, because they are kind of tricky. Well, this limit is a little bit tricky. This one is quite easy, because if we plug in 1 for delta, then we have 1 here, and we have 1 times y, which is just y, so all we get here is y to the power of n times 1 divided by n plus 1 times the log of y. So we can just delete this whole thing here and put this thing here instead. And we can also write that a bit cleaner with a y to the power of n here in the numerator. So let's shift that so we have some space for the rest. Now, I said this one here is a little bit tricky, because if we plug in 0 for beta, then we have 0 here, and then we have infinity here. So this thing here is of the type 0 times infinity. It's also similar to the function x times log x, because we have beta times log beta, but the beta here is to the power of n plus 1, so it's like x to the power of n, but it's already sufficient to only deal with the function x times log x. And we will look at the limit for x going to 0, and this is exactly the limit that we are having here. So we apply L'Hopital's rule, but we cannot apply it right now, because first we have to make a fraction out of the whole function. So we have log x divided by 1 over x. This is the trick. Now we take the derivatives of the numerator and of the denominator. So we have the limit x going to 0, and then we have 1 over x in the numerator, that's the derivative of the log, and then we have minus 1 over x squared. And this eventually gives us x going to 0 of minus x, and this is just 0. So the whole term here goes to 0. Amazing. So we can just drop it completely. We can completely delete this and save some space for the last integral, which is this one here. So let's have a look at this integral. This integral is minus the lim of beta going to 0, delta going to 1, times beta delta y to the power of n, x to the power of n plus 1 divided by n plus 1, 1 divided by x dx. And of course we can't just cancel that out, and then we have an x to the power of n here. And integrating is fairly easy because it's just a polynomial. So we have y, we have the limit of beta going to 0, delta going to 1 of y to the power of n, x to the power of n plus 1 divided by n plus 1 squared, and the whole thing evaluated at delta and beta. And this just gives us, if we plug in the limits, y to the power of n divided by n plus 1 squared. So that's what we can write here as a solution for the integral in blue. So we have minus y to the power of n divided by n plus 1 squared. This is the solution for our x integral. Now we just have to plug that into our y integral, the whole function. The y integral was alpha going to 0, gamma going to 1. The limit also was from alpha to gamma. And then we use the whole function here and plug that into the integral. And that's what we have to solve now with respect to y. All right, so we have two different integrals here, so let's write those two different integrals, alpha going to 0, gamma going to 1. Then we open the brackets. We have the first integral, alpha to gamma of y to the power of n divided by n plus 1 times the log of y dy, minus the second integral from alpha to gamma of y to the power of n divided by n plus 1 squared dy. So let's have a look at those integrals separately. First integral, this one, once again, we will have to apply integrating by parts, but this is fairly easy. So we have the limit of alpha going to 0, gamma going to 1 of, now we open the brackets again, and now integrating by parts means we have y to the power of n plus 1 divided by n plus 1 squared times the log of y, and the whole thing evaluated at gamma and alpha, minus the integral of, and now we're going from alpha to gamma, then we have y to the power of n plus 1 divided by n plus 1 squared times the derivative of the log, which is 1 over y dy. So this is our integral. We can drop the 1 over y already and the plus 1 in the denominator. Then we shorten the integral already and the bracket finishes a bit earlier. Now we have to take a look at those limits here again. So what happens if we plug in 1 for gamma? What happens if we plug in 0 for alpha? So let's plug in 1 for gamma. 1 for gamma means that this is 1 and this is also 1, but log of 1 is 0, so the whole thing is 0. Nice, the whole thing flies out. Perfect. Then the second one. The second one is we plug in 0 for alpha. So we have a 0 here, and this is a 0, so we have a 0 here. This gives us minus infinity. We have the same problem again, 0 times minus infinity, but we already solved that with L'Hopital, and we know this gives us 0 in the limit, which means that this whole thing is 0 and can be dropped completely, and we can drag this thing here and open the brackets, and now we can also put in the integral from above, so this one again. So let's copy, put it down here, and delete one of the brackets. So let's solve those two integrals. That's like one of the last steps that we have to do until we get the final result. So don't worry about the minus, because I already told you that the function will be minus 2 times the zeta function of 3. So this minus is correct. Don't get disturbed by that one. So we have limit for alpha going to 0 and gamma going to 1. So the first integral, we integrated with respect to y. This is also very simple again. So we have y to the power of n plus 1 divided by n plus 1 to the power of 3. And the whole thing evaluated at gamma and delta minus, and now we have once again y to the power of n. That's the same integral, so actually we don't have to write that again. We can just put a 2 right here. All right, we're almost done. Now we plug in 1 for gamma and 0 for alpha, and we will see that this is minus 2 times 1 over n plus 1 to the power of 3. This is the final result for our double integral, but what is missing is the sum, because what we had is when we look up here, where did I have that? Where was it? Ah, no, that was not it. The sum, where is it? Ah, yeah, here. I'm blind, I'm sorry. So here, We have solved the whole double integral here, but what we're missing now is that sum sign. We have already dealt with the limits here, but we are missing the sum sign. So the final result is that the double integral from 0 to 1 of log xy divided by 1 minus xy dx dy is equal to minus 2 times the sum from n equals 0 up to infinity of 1 divided by n plus 1 to the power of 3. So we're almost there. This is minus 2 times the sum. Now we perform an index shift. Just we start at n equals 1, going up to infinity. Then we have n to the power of 3. And this thing here, this is the zeta function of 3. And this is why this integral is equal to minus 2 times the zeta function of 3. This is the final result. I enjoyed this calculation so much. This is so amazing because applying all those different methods like integrating by parts, improper integrals with limits, using L'Hopital's rule, using geometric series, using double integrals, and then getting such a magnificent result. Like it's the Apéry constant, you know, like that's so amazing. Yeah, let me know in the comments what you think. If you enjoyed this calculation, leave a like, subscribe to my channel if you haven't done that already. You know all of this, you hear it all the time, but it helps me a lot. And yeah, see you in the next video. Bye, my fellow path integrator.